Alright, so as we move through these Chapter 14 topics, we want to address polyprotic acids. We just did a shortcut video that will apply to ice tables from here on out. So when we start to do ice tables for polyprotic acids, we can definitely use that material. So let's get into the polyprotic acids. So between Gen Chem 1 and Gen Chem 2, we've talked about several different classification schemes for acids. We've talked about the binary acids like HCl. We've talked about oxyacids. We have talked about the weak and strong classification schemes. But now we want to talk about acids in terms of how many protons they have. So we have monoprotic acids, mono meaning one. We have diprotic acids, where the di means two. Triprotic, where we have three. And poly is just going to indicate that there's more than one proton. So polyprotic, or many, poly for many, is just saying that you really have more than one. So diprotic acids and triprotic acids can be referred to as polyprotic acids, and that would just be in contrast to the monoprotic acids, which only have one proton to give up. And so in each one of these naming conventions, protic is referring to protons, so many protons, versus just one proton. And so if we want to build that out, some examples of monoprotic acids are definitely going to be those binary acids, things like HCl or HBr. They have one hydrogen that can be donated. We also had some of the oxyacids, like HNO3. Nitric acid is a oxyacid, but it still just has that one proton that it's capable of giving when it gets into solution. Diprotic acids, we need examples that have two hydrogens, so something like an H2SO4 would be an example of that. A triprotic acid would be something like phosphoric acid, H3PO4, and then polyprotic, again, we just refer to either of these two classes. So ionization occurs in steps. So what we would do is we would look at the initial acid. So phosphoric acid is the one that's been given us in this example. So phosphoric acid, we just said, was a triprotic acid. We can reconfirm that for ourselves because we see that there are those three hydrogens. And so this molecule could actually lose up to 3 protons, but they would happen in steps. So step 1 would be the loss of the first proton. So if you mixed phosphoric acid with water, we would get one of these protons to jump off of phosphoric acid, jump onto water, and that would give us that H3O. Now, as a consequence, H3PO4 would now become H2PO4. So that would be step 1. In step 2, what was produced as a product last time, H2PO4, would still look like a molecule that could donate a hydrogen to water. So now we would start with H2PO4. If we added that together with water, again, a proton would jump off of that molecule and could jump onto the water molecule. That would leave an H1PO4, right? And it would give us another H3O. We could still look at this product molecule, HPO4, and say it still has a proton that it could give away. So we could actually do a third step for this triprotic acid and say that this HPO4 molecule could donate that proton. That proton could jump onto water to make an H3O+. That's going to leave no more H's. This is not a tetraprotic acid. This is a triprotic acid. We've gotten rid of all 3 H's, so all that's left is that PO4 3-, that phosphate ion. And we did, in fact, transfer that hydrogen onto a water, so we have an H3O. So for a diprotic acid, we would actually have 2 steps. In this example, with a triprotic acid, we had 3 steps. So if we wanted to do the stepwise ionization of sulfuric acid, now we would have a chance to employ what we just learned on the previous slides. Now would be a good point to pause this if you wanted to work it out yourself. And then we can go ahead and start to work it out together. So for sulfuric acid, we have H2SO4. That is the formula for sulfuric acid. So in the first ionization event, we're going to take this nice neutral compound, H2SO4, and we're going to say that one of the protons is going to jump onto water to form H3O. What's going to be left is going to be HSO4. Now that molecule still looks like it can give up a proton, so we could write a second step, a second balanced chemical equation saying that now we have that HSO4. That HSO4 still has a proton that still wants to jump onto water. When that occurs, we're going to make another H3O, and we're going to be left with an SO4 molecule, a sulfate molecule in this case, and that molecule no longer has any protons to give away, and so that would be the reason this stops at 2 proton donations for this diprotic acid. But what does that mean for the dissociation constants, those ionization constants like Ka? What does that mean for the overall pH of a solution when you're dealing with a diprotic or triprotic acid as opposed to just those monoprotic acids that we've primarily been dealing with? So for each one of the hydrogen transfers, for each one of the proton losses, there's going to be a dissociation constant. So for that first step, where we're losing a proton, we could call this Ka1. So we are going to have a dissociation constant saying that there is some fraction of H2SO4 that's going to ionize in solution. We could then describe the second step and say the product from the first step, HSO4-, is going to be our starting material for that second step, and now there's going to be a different dissociation constant when this new molecule, HSO4, loses its proton. So this inherently means that if we have 2 different Ka values, that H2SO4 wants to give up its proton differently than HSO4. These molecules don't give up their protons at the same rate or in the same proportion. So then a logical question is, how are these 2 Kas related? How is Ka1 related to Ka2? How is the dissociation of one proton related to the dissociation of that second proton? So as we go down from step 1 to step 2, is the Ka going to get larger or get smaller? And why? Again, if you want to pause it, try to think about that, work it out, great. If not, we can go ahead and work it together. So in the instance with H2SO4, giving up the first proton is actually pretty easy. So H2SO4 we consider to be one of our stronger acids. And so when it gives up that first proton, that is an easy step. So if it's easy to give up that first proton, that means that this Ka is going to be larger. Now when we're left with HSO4, now we're talking about giving up that second proton. It's actually more difficult to give away the second proton. And so because of that, that Ka value is actually going to be smaller than the first Ka value. So as we go down in steps, it gets harder to give away the proton, and that means that we're going to end up with smaller and smaller and smaller K values as we go further and further steps. So if we reflect back on the phosphoric acid example, there were 3 steps. The first deprotonation, that first donation of a proton, is going to be the easiest. That is going to be the largest Ka value in that sequence. When we try to give up the second proton, our Ka value is going to get worse, it's going to get smaller. And then when we try to get to that third proton to give it away, it's going to be even harder to get rid of that proton, which means that you're going to end up with a Ka value even smaller. So that might mean something like times 10 to the minus 5 for the first one, and then this next one is maybe times 10 to the minus 10, and then maybe for our example with a triprotic acid, maybe that third proton trying to give it away might be something like times 10 to the minus 20, right? It's going to continue to get harder and harder to give these away. So that brings up another logical question. So if we have these different Kas, and each Ka means we're donating additional protons into solution, how do we calculate the pH of the overall solution? If I just put H2SO4 into solution, I actually have to account for the protons that come off for the first dissociation and the protons that come off for the second dissociation. So what we would need to do if there are multiple Ka values is come in here and say, okay, Ka1 is going to be responsible for putting in some amount of protons into solution. So we'll say those are the protons that are associated with Ka1. And we would need to use an ice table in order to calculate that. And we've been doing that all along, so we're not going into that here. But then what we would need to do is we would need to consider what would happen with Ka2. Ka2 is also saying some even probably smaller amount of H3O plus is going to go into solution because of Ka2. So the ice table from Ka1 is going to give you a product that is missing an H. That product that's missing an H is actually going to come over here and be the reactant in your next ice table, right? So now that product is going to become our reactant for the second Ka, and you are going to have to plug that into the ice table. This second ice table is going to give you another H3O plus concentration, and you are actually going to need to add those together in order to come up with a total H3O concentration. And once you have that total H3O concentration, you can actually calculate the pH, right? Because we want to take the negative log of what would essentially be the total H3O concentration in that solution. Now, for all practical purposes, that second ionization usually doesn't donate enough protons to really change the number versus the amount of protons that went into solution with the first donation of a proton, but we'll see that in the next examples, and usually you'll see that when you round for sig figs, everything that happens in that second ice table can kind of go away. So instead of asking in these questions just for the pH, which you might be able to get from one ice table, they'll typically ask you for, the concentration of different ionic species, because then you actually have to solve the second ice table to get an X value and plug that in to the table. Okay, so a little bit different things that they'll ask you when it comes to these problems, because they want you to solve two ice tables. So that's going to wrap up this conceptual portion of polyprotic acids. We've talked about conceptually what we're going to have to do in order to calculate pH or the concentrations at equilibrium of these different ionic species, but I'm actually going to work some of those problems in the next section of the lecture. So you're welcome to go ahead and close this one and then fire up the next one when you're ready.